Okay, good evening, everybody. Welcome. Okay, so without further ado, we'll launch into the first of this academic year's talks, and it's my great pleasure that we were able to get one of our relatively new members of faculty to come and tell everybody what he's doing, including me, which is great. It's Dr. Jacob Dunningham. Now, Jacob, you'll be able to tell from the way he speaks, he didn't originally come from England. In fact, he did his undergraduate studies in New Zealand, and then came here to the UK to seek his fortune, or at least a PhD at the University of Oxford, and then came here via as a reader via the University of Leeds. So I'm going to figure out just how to switch to his laptop, and hopefully the title of the talk will appear. And his talk is about a fascinating subject of how quantum physics is revolutionizing technology and thereby our lives. Okay, thanks very much.
Thank you. Still seeking my fortune, but hopefully this will lead to it. Who knows? Thanks everyone for coming out this evening. It's great to see so many people here. I hope I make it worth your while. It's a real pleasure for me to be able to tell you about some of the research that I've been doing recently, and indeed a large number of people have been doing all over the world. So the subject of tonight's talk is quantum physics, which usually conjures up ideas of weirdness, haziness, and difficulty. I'm hoping that I will get rid of at least two of those tonight. I hope some of the haziness will go away. I hope I will convince you that it's not really so difficult. In fact, in the next 40 or 50 minutes, I want to tell you everything you need to know about quantum mechanics. So those of you who are coming to my atomic physics course, it's all here. I also want to, I mean, the weirdness will remain, I'm afraid. It just is weird. There's nothing we can do about that. So I'm going to have to ask you to suspend a little bit of disbelief about some of the things I tell you. So it's a very interesting area. It's an area that is getting a lot of government funding at the moment. The government has just recently announced several £100 million of extra funding that go into this. And many of you are taxpayers, so thank you. There's my fortune. But I think it's an interesting area, and it's something, given that many of you are funding it, it's something that you should perhaps know about and see what we're doing with that money. So I'm going to try and explain everything tonight only with pretty pictures and I was going to say no equations. There's two, but I promise you, all of you will have seen these equations before. So hopefully, you know, I've got a lot to get through. If I talk very fast, you'll know why. I've called the talk Making Use of Uncertainty, which might strike you as slightly odd because surely science is about getting rid of uncertainty. This title was actually given to me by the organizers of a talk I gave at a philosophical society a while ago. And originally I thought, what a terrible title. How can you make use of uncertainty? Science should do the opposite. If you're a politician or a lawyer or a military general, you might want to make use of uncertainty to gain an advantage, but science should do the opposite. But actually you find that when you delve down into the depths of quantum mechanics and the fundamental structure of the universe, you find that it is fundamentally random. And although this is a bit unsettling when you first see it, we shouldn't run screaming in horror, but we should embrace it. And this uncertainty really is a friend rather than a foe. And I hope to convey to you tonight that we can make use of this uncertainty, and it actually enables us to do things that we wouldn't have been able to do otherwise. So it actually is a great advantage having this uncertainty. So let's launch on and tell you all about quantum mechanics. We're going to start 100, 150 years ago with two very different characters. Lord Kelvin, a very famous physicist who was one of the pioneers of thermodynamics and so gave us a lot of the Industrial Revolution, so a very important figure. And Josiah Wedgwood, who is not a famous physicist, but a very well-known ceramicist. His company, Wedgwood, is very well known and very successful today. So A little over 100 years ago, Calvin was giving a public talk in London when he essentially said that all physics is over. There's nothing new to be discovered. All that remains is more and more precise measurement. It was a comment that really came back to haunt him. He'd glossed over the fact that there were a couple of little chinks in the armor, a couple of little things that physics at the time couldn't explain, but he thought physics would sort it out eventually. And one of those chinks was something that was noticed by Josiah Wedgwood. He noticed that when you put clay into a kiln and heat it up, it would glow. We know that. You stick a poker in a fire and it can glow red. If it's a hotter fire, it might glow orange or yellow or white or even blue if it's an extremely hot fire. And Wedgwood noticed that the color was connected to the temperature of the kiln. So an experienced potter could just look at the color and say, yeah, that's the right orange. This plate should come out just fine. So it was sort of a thermometer just looking at the color. And in fact, he even noticed that it didn't matter what you put in the kiln, it always glowed with the same color. So it wouldn't matter if it was metal or clay or something else. And this, I think, is quite intriguing, but it's particularly intriguing because it was the thing that unpicked classical physics at the time, because classical physics could not explain it. Try as they might, the classical theories came up with a completely different explanation that showed that you should have infinite amounts of very high energy radiation. Okay, so classical physics was completely wrong. And to cut a long story short, they found that they had to revise all of physics and come up with this whole new theory called quantum theory. And quantum theory changed everything. So these tiny chinks in the armor that Calvin had overlooked really did change everything. So I'm now going to skip forward 100 odd years. I'm not going to go through the development of quantum theory. It's a very interesting subject in its own right, but I want to go straight to the nub of what they found and to condense into two short statements what quantum theory is all about. So really, this is everything you need to know about quantum theory, at least for the purposes of this talk, and for the purposes of most things, actually. This is all you need to know. First thing is that events are completely random. Okay? Fundamental events in the universe are completely random. And the second one is that objects can be in more than one place at a time. Okay, so there's some weirdness here, and this is the weirdness that I'm not going to be able to get rid of, but hopefully when I talk about it, you'll at least see what the consequences are and get a feel for what this all means. So the first one, events are completely random. I mean, how can this be true? The world we see around us is not completely random. We see, you know, they say taxes and deaths, you know, completely predictable. The sun comes up every morning. There are certain things in the world that we can predict. So how can everything be completely random? In fact, how could we do science if everything was completely random? Because science is about finding patterns and making predictions about the world. So if everything was completely random, then we should give up and go home. But we know this isn't true. So let me try and explain what I mean by this and how we can get a predictable universe out of something that's completely random. In fact, there's a bit of a paradox. Quantum theory says everything's random, but quantum theory is also the most precise scientific theory we have. It can make predictions to 1 part in 10 billion. It's incredibly precise. To give you an idea of the context, that's something like measuring the distance between London and New York to within the width of a human hair. So it's pretty good. So let me tell you about what we mean by random events. So I'm going to illustrate it by means of a very simple experiment. It's about the simplest experiment you can imagine in optics. It consists of a piece of glass, which is given the fancy name of a beam splitter, and a particle of light. So we can think of light as a stream of little particles, and they're called photons. So we've got a photon, it hits this beam splitter, and it does something. Well, you'll know from looking through windows that sometimes you see what's outside the room, so you see light coming through the window, and you might also see your face reflected in it. So light, when it hits glass, can pass through it, or it can reflect. So it can take these two different directions, and in fact you can arrange it by putting just the right amount of silver on the glass so that exactly half goes through and half is reflected. So what would happen if I shone some light at this? Well, you'd expect half the light to go this way and half the light to go that way. So we have a stream of photons, we fire them through and we see some nice flashes going on, and I've tried to depict that as a bit of a random process. Sometimes it goes one way and sometimes it goes the other way. And I should say that this photon isn't broken into pieces. It always remains as a whole particle. So when it goes through the beam splitter, I don't splice it into two parts, one half going one way and one half the other way. It's always the whole photon one way and the whole photon, or the whole photon the other way. So it's a very random, it turns out it's completely random. It's like a coin toss. But it's more random than a coin toss. A coin toss you can always cheat a bit. Apparently, whatever side, you know, if you toss it in the usual way and catch it like that, whatever side is facing up, I think, turns up about 3% more likely than the other side. So you know how to call it next time you're, unless you're against me, because you know what I'll be calling. But you can't cheat this. This has been tested by code breakers and various government agencies to see if there is any pattern in the output here, and they can detect nothing. So the most sophisticated algorithms for pattern spotting have found absolutely no predictability in this. And this should be quite concerning, because this is the simplest, pretty much the simplest experiment I can dream up in optics. One particle of light, one piece of glass, and physics hasn't got a clue what the outcome of it is. So it's not boding well so far, but you know, this is illustrating the randomness of this. Oh yeah, little bit cartoon. Actually, finding whether things are random is not always that easy. So here we've got this guy. Over here we have our random number generator, 99999. Are you sure that's random? Well, that's the problem with randomness. You can never be sure. Actually, it is very hard. If you try and compare a string of random numbers where one of them is somebody tossing a coin and somebody is just making up heads or tails, it is actually quite hard to compare. You tend to find that humans try and be more random than they ought to be, and they don't like doing a whole string of 8 heads in a row if they're just making it up. So actually that's usually the way you tell. But there are nice algorithms that national agencies have for spotting these things. And as I say, what we saw before is essentially, you can think of it as a random coin toss, the most random coin toss we know of in the universe, something that you can't cheat. Okay? That's all you need to know for now. And so this seems pretty useful. One way it might be useful is that we can create genuine random number detectors, generators I should say. Your computers and so on have random number generators on them, but they're not random at all. They repeat after a while. Tossing a coin can be cheated, as I said. So it'd be nice to have something that is a genuine random number detector, and we can use quantum physics to do that. In fact, there are now commercially available devices that do this. They do essentially what I described on the previous couple of slides, to generate true random numbers that are used for, well, you can guess, mainly the gaming industry, actually, the online gaming industry. There's a lot of these in Las Vegas, and there's a few companies that are set up to generate these things. So that's your first quantum technology. You might say that that's not the most profound or worthwhile one, but still, random numbers are also useful for other things. So hopefully I've convinced you that quantum events are random. Now I want to try and describe to you how it is that we see order in the world around us. Why is it that the underlying fabric of the universe can be random and yet we see predictable events? And so I'm going to do that with a slightly more complicated experiment. And this is the most complicated thing I'm going to show this evening. It consists of 2 of these beam splitters, so 2 pieces of glass that are arranged in the way shown. And we're going to shine some light, maybe a single photon or maybe a whole stream of them, and they're going to reach this first beam splitter. They will either transmit through it or reflect. And whichever way they go, they're going to encounter one of these, which is just an ordinary mirror, which is going to reflect it back to another piece of glass, another beam splitter, at which it's going to again transmit or reflect. Okay? So I've got 2 completely random coin tosses, one after the other. That's the idea. So what would you expect to happen? Well, I know what I'd expect, and I know what most people expected, and that was that you would put a particle in, it would randomly go this way or this way. Whichever way it goes, it randomly goes this way or this way when it gets here. So you should see the photon half the time here and half the time there. Okay? 2 random things give a random thing, right? Well, there's a big surprise, and if we do the experiment, we see something like this. We see some flashes, but after a while we notice something strange going on, and that is that the flashes always go the same way. And it doesn't matter how many times you do it, the flashes always go here and never go there. So we're getting something completely predictable from 2 completely random things, so random that Las Vegas is prepared to stake their fortune on it. That's how random it is, and one after the other, and we've got something completely predictable. By the way, we haven't worked out how to fix these machines in Las Vegas. I'd be on a beach in the Bahamas probably if I had. No, I wouldn't. I'd still be doing this. Nice thought, though. So how is it? You know, to put it in another context, it's like having two coins. This one is completely fair. I toss it, I get 50-50 heads and tails. This one is completely fair. I toss it, I get 50-50 heads and tails. I toss the two together, and they both always come up heads. Okay? So it's a weird thing. There's no classical analogy of this. So what I want to do is to try and explain why this is the case and show how the underpinning physics behind this leads into some interesting quantum technologies that are already changing our lives but are going to have a huge impact on our lives, I think, in the next 20 or 30 years. So to do this, we need to think a little bit more about light. So light can be described as a particle, as I've described, but it also can be described as a wave. And in fact, this is a property known as wave-particle duality. Sometimes it's one, sometimes it's the other, sometimes it's a bit of both. And I think I found this graphic, which I think is quite a nice way of illustrating it, sort of. It's, if you squint at it one way, it says light is a wave, and you've got to look a little bit harder to see that if you look at it another way, it says light is a particle. So anyway, it sort of embodies this duality of the two things. I think it's quite a clever way of doing it. So you know about water waves, right? You tap the bath water and it makes little ripples, as shown over here, and when those waves come together, you find that you get interesting behavior. That sometimes the waves add up and give a bigger wave, and sometimes they cancel out to give nothing, and you get interesting patterns. So understanding those patterns is quite important to this. So let's think about this. So imagine we have two different waves, a red one and a blue one, and imagine they are arranged in such a way that the peaks of one line up with the troughs of the other, like this. Then what happens is they tend to smooth each other out. The extra water here fills in the gap there, and vice versa, and they cancel out to give nothing. So you can probably find little patches here where the waves have cancelled out to give nothing. The other extreme is when the peaks of each of the waves line up. And then you get big peaks and big troughs, and you get a very large wave. This is known as constructive interference. Okay, so these two effects are going to be important. The one other thing that you need to know, and you'll just have to accept this unless you want to do a quick course on Maxwell's equations, is that when you reflect a wave from a surface, it shifts, the wavelength shifts by a little bit. In the arrangement I'm showing here, it shifts by a quarter of a wavelength when it reflects. When it passes straight through a medium, it doesn't shift at all. Okay, just take that on faith, hopefully. So with that in mind, let's see if I can describe how this strange occurrence happened, how two completely random things gave something completely predictable. Well, let's think about the possible ways that the photon could have got to the place where we always found it. Remember, we always found it here. Well, it could take this red path, or it could take this blue path. They're the only two ways it could go. You can convince yourselves of that. This red path reflects once, twice, and this blue path reflects once, twice. Okay? So each time it reflects, the wave shifts a bit. So let's see what happens. The red wave starts like that, shifts once, twice. So it started off as the black dashed one. Let's just go back and show you. Starts off there, shifts once, twice. And the black dashed one is just to show you where it started. Okay? Let's repeat that for the blue one. It starts off there, it shifts once, twice. Here, the two waves are on top of each other, so they add up, and you see that the peaks add up and the troughs add up. And so what do we get? We get a big wave. So that's why there's a lot of light there. A big wave equals lots of light, right? What about the other case? Why do we never see any light there? Well, again, let's use a similar analysis where there are two possible ways the light could have got there. Of course, none ends up getting there, but there are two ways it could have got there, this red path or this blue path. The red path reflects 3 times and the blue one once. So let's see what happens with the waves here. If we start with the red wave, it shifts 1, 2, 3 times. And the blue one starts off here and it just shifts once, like that. You see that? And now if we add those two up, you can see what's going to happen, right? the peaks of one line up with the troughs of the other, and we get nothing. Okay, so that explains in terms of waves and interference why we see all the light over this way and nothing over there. But, you know, where's the mystery gone? You know, because it seemed very strange. We had this randomness, and now it seems to have a perfectly plausible explanation in terms of interference of waves. Well, the mystery is that we can do this with a single particle of light. When we interfere waves, we have a huge number of water molecules forming waves, overlap with each other, and we get interference. Here, we can see the same effect with a single particle of light. And remember, a single particle of light cannot be split, so half goes this way and half goes this way. So what's interfering with what? The whole photon takes this path, or the whole photon takes this path. So what's interfering with what? How do we get two waves? Well, the explanation is that that use of the word or was wrong. The photon takes this red path, and the whole photon takes that blue path. There's only one photon, and we're not splitting it, but the whole photon goes one way, and the whole photon goes the other way. So this is the weirdness. This is the weirdness that I can't get rid of, I'm afraid. As some people like to say, and I think this is this is possibly even more weird, that if you don't like that, then you can say, well, this piece of glass splits the universes, and in one universe, the photon goes this way, and in another universe, the photon goes that way. And then this piece of glass recombines the universes. So if you prefer that, then that's fine. I know that Stephen Hawking says that whenever he hears that explanation, he reaches for his gun, and it's also been said that it's short on assumptions, but expensive on universes, that explanation. So I'll let you take your pick on which one you prefer. But either way, it's weird. That's the only way we can explain it, is that somehow something is happening in two places at the same time. Okay, so this is all very intriguing. Is it useful for anything? Well, yes, it is. This process is the underpinning to a whole lot of quantum technologies that are being developed at the moment. So I want to start by illustrating how this setup could be useful for something. It's a slightly contrived scheme, but it will illustrate the sort of things we might be able to do. So imagine the following scenario. Imagine that there's a package, a brown paper package, turns up at number 10 Downing Street, addressed to the Prime Minister, with a note on it saying that there's a bomb inside the package. And it goes on to say that it's not just any ordinary bomb, it's a quantum bomb. It's from a group of disillusioned physicists who are angry about something. And they've invented this quantum bomb and decided to set it to number 10. And it has to go on to explain, of course, what a quantum bomb is. By the way, they don't exist, don't worry. But it says that it's a bomb that's so sensitive that if a single photon hits it, it will explode. Now, this is a problem because, as I understand it, when there's a bomb threat, the bomb disposal experts come in, they look at the package, they try and ascertain whether it's a hoax or there's a real bomb in there. If it's a hoax, they go home. If it's a bomb, they, I don't know, do a controlled explosion or whatever they do. But this one, in order to tell whether it's a hoax or not, you have to look at it. And in order to look at something, you have to scatter at least one photon off it, right? I mean, at the moment, millions of photons are entering your eyes, they're scattering off the screen, off me, off everything. I think humans can see down to 10 or 12 photons. We have pretty good eyes. Cats can see down to about 3. But the fact remains, even for a very precise device, it needs to measure at least one photon in order to see something. And if we scatter that photon off the package and there is a bomb there, it goes off. So the question is, can we tell whether there's a bomb in the package without ever looking at it? Okay? I mean, statements like that just seem absurd in the classical world, but actually in the quantum world, they're not. And the answer is yes. It would be a damp squib if I told you no at that point after building it up so much. The way we do it, though, is like this. We put the suspect package in one path of this device that we've studied, and let's consider some different scenarios. So let's start by considering the case where it was all a hoax. So there's no bomb there. We can imagine that package isn't there at all. Okay, I'm simplifying things a bit. Imagine it's not there. And we know in this case that the light always goes this way. Remember from what we saw before? Okay, so a hoax, always light there. What if it's not a hoax? What if there is a bomb in the package? Well, there's two different things that could happen here. The photon comes in and it reflects or transmits. If it transmits, it hits the package and the bomb goes off. So that's not so good, but it happens sometimes. It's dangerous job, this. Let's focus on the more positive side. Sometimes the photon reflects and it comes up this way. And when it gets to this beam splitter, we know what happens. It's a random coin toss, 50-50, that way or that way. So look what's happened. When it's a hoax, we always get the light there. When it's a real threat, sometimes the light is there. So when this detector starts clicking, that's telling us, watch out, there's a bomb. And what's really weird about this is if you look at what path the photon has taken, it's taken this red path. It's gone absolutely nowhere near the package. Isn't that weird? It's like being in a completely dark room with a flashlight, shining it that way, and being able to see something over there. It's really weird. This really works. Experiments have been done on this. They're used to image samples that are very delicate. They're not for quantum bombs, but let's say you have a very delicate biological sample that you want to image, but you don't want to shine any light on it because it'll damage it. Well, you can see it without shining any light on it using this sort of technique. It's amazing, isn't it? And this one has a 50-50 death rate. You can actually arrange this so that you have a infinitesimally small death rate and approaching 1 probability of knowing whether the bomb is there or not. So this gives you an idea of the sort of things that weird quantum rules enable us to do. We can see without looking. The idea of this is something called non-locality. It's called non-locality because something here can affect something over there, something that is not local to me. And that's going to turn out to be a very important aspect in some of the things I say later in this talk. So this bomb can affect something about the light that is nowhere near it. Okay? It's a non-local effect. So how far can we go? We always want to push things further. You know, why stop there? We can do it with light. Light is small. Light is easy. That's for, you know, that's for beginners. How far can you push it? Well, it's been done for electrons. It's been. Oh, this is taking. It can be done for neutrons, and it has been done for neutrons. It can be done for atoms. It can be done for molecules. So a lot of work has been done on looking at putting fullerene molecules, which are like footballs made up of carbon atoms. So little footballs, putting them into superpositions, have been in 2 places at once. Experiments are currently going on, largely in Vienna, but also in Southampton, just along the coast, trying to push this to larger and larger molecules, especially things like proteins, because wouldn't it be great if we could start making biological things in 2 places at once? Because you know where we're heading with this, right? We want to do it with people. No, we don't. Well, you know, who knows, one day. But wouldn't it be nice to start seeing quantum effects in biology? So the current record is somewhere between these two, actually. And it's also been done with mechanical devices. So you can imagine a little metal flap, a little lever. It's hard to see here. It's a little thing here. It's quite small. It's about a nanogram, 1/1000 of a gram, but still pretty big by quantum standards. And this is being put into a superposition of vibrating, like this, and not vibrating. So the whole thing is vibrating, and at the same time, the whole thing is not vibrating. So people are playing games with things like that, which are kind of fun. So I've talked about an arrangement of beam splitters that show light taking 2 possible paths. Another way of doing it is having a screen with 2 slits in it. And if you shine light at those 2 slits, then you can see an interference pattern behind it. That is, you see places where the light definitely goes and places where it definitely doesn't go. And this is an indication of the light going through both of those 2 slits at the same time. I've got a diffraction grating thing here. Hopefully this will work. This is the most advanced experiments I ever do. So hopefully you can see a bright central spot there and 2 faint ones off to the side. It was better here, wasn't it? Can you see that? So there's a central spot and 2 off to the side. So it's interference effects that are going on in that. There are slits in this that is enabling the light to go through, and the fact that I'm seeing this structure of lots of regions where the light isn't and certain regions where it is the same as this arrangement of beam splitters. So it's it's telling me that the light is going through more than 1 slit at the same time. So that's the idea done behind, that falls behind these experiments, looking for interference fringes. So I explain that just so I can show you some recent experimental data, which is showing a slightly larger version of this. There's something in between these 2. And what you do is you set up a double slit experiment, you fire these molecules at it, and you wait. And you wait a long time, and not that long. You wait this long. After 5 minutes, you see a few dots on the screen. Doesn't tell you anything. After 50 minutes, you see some more. Still not much. After an hour, not much. Hour 40. 4 hours, you might start to see some stripes there. 8 hours, perhaps a bit clearer. 16 hours, some quite clear stripes, I think you'll agree. At 42 hours, some nice clear stripes. So this is all done for full-ring molecules and is experimental evidence that these are being put into more than one place at the same time. There's no other way of explaining these interference fringes. So I just want to stress, I guess, that as far as we know, there is no limit to how large an object can be and to undergo this quantum behavior. Many of you will have heard of Schrodinger's cat, this paradox where you have a macroscopic object, namely a cat, that's put into a superposition of being alive and dead at the same time. It's the same sort of idea. Okay, people are pushing this towards cats. We've got to get to mice first, but you know, we're getting there. Proteins in mice, then cats, then us. Who knows? One of the nice things about being a physicist is you get to go to nice places for conferences, including ski conferences, where people are in their ski gear and ski out the chalet at the end of the talk. So some students at this conference I was at decided to depict Schrodinger's cat in snow. So we've got for the experts here, you can see the bras and cats there, and for everyone else, there's a cat that's alive and a cat that's dead there. So essentially, it's seen where the macroscopic objects can go through double slits at the same time. So it's really doing this, although it's not really doing this, I should hasten to add. But that's the idea, is whether macroscopic objects have wave properties and can be in more than one place at the same time. So, what's all this good for? Why is it it's just an ego? Well, it probably is just an ego thing. Why push to bigger and bigger things? Why do we want to make bigger and bigger superpositions of objects? I guess on one level it's to test the underlying theory, and there are some fringe theories that suggest that maybe you won't be able to do this when things get larger than a certain size. So it's fun to play around with for that reason. But I'm of the school of thought that everything eventually, if you wait long enough, becomes useful. So I justify my research anyway. I like this quote from George Porter, who was a Nobel Prize-winning chemist. He said that all research is applied or yet to be applied. I think that's very true, and I think that's a clarion call for fundamental research and why it's useful and why it's important. I love this paper. If a quick Google search will bring it up, The Usefulness of Useless Knowledge. Again, another treatise on why just doing anything is worthwhile eventually. You know, wait long enough and you never know, you'll find a use. But to be a little bit more serious, why do we want to make these large superpositions? Other than studying fundamental physics, which of course is interesting in its own right, well, we can do very useful things with them. And this is something that's actually from my own research, is that I'm interested in creating flows of atoms. So very cold atoms, you can create a flow of them that behaves as a superfluid. That is a fluid that once you stir it will just rotate forever. It's got no viscosity. But if you're even more clever with it, you can arrange it so that the atoms are flowing in one direction around a loop and at the same time the other direction around the loop. So you might have 1,000 atoms, all of which are flowing clockwise and all 1,000 of which are flowing counterclockwise. So it's not each one is going both ways. It's not that half are going one way and half are going the other way. All of them are going one way and all of them are going the other way. So it's a bit like a Schrodinger cat state where the whole cat is alive and the whole cat is dead at the same time. And this is useful because it turns out that it's incredibly sensitive to little rotations. So it turns out that it has great promise as a very precise gyroscope, which could be useful in inertial navigation systems and so on. Okay, so we've talked about things being in more than one place at once. There's a small step from that to go to the deep fundamental underpinning of all quantum technology, which is a concept called entanglement. And actually, it really is nothing more than what you've seen already. The only other idea we need is something that you're familiar with, and that is correlations. So in the everyday world, we know that things are correlated. We know that, I don't know, you don't get enough sleep, you're correlated with being tired the next day. You drink too much the night before, you feel a bit rough the next day. You know, you work hard for your exam, correlated with a better mark in your exam. There's correlations in the world that we're all familiar with, right? So I'm depicting some correlations here in a simple way, two particles, and they can be pointing up or arrows down. And these two particles are perfectly correlated. If one points up, the other one points up. If one points down, the other one points down. So that's the classical world. In the quantum world, we can have weird things. We can have things where I didn't drink too much last night, and I did drink too much last night. I think we've all, experienced that. But, but here, we can have a particle that is up and down at the same time. And whichever state it's in, it's perfectly correlated with the other one. So we end up with a situation like this, where we get both up plus both down. And this is known as an entangled state. These two particles have a certain type of quantum correlation between them. And what's weird about these is that one person, let's call her Alice, could have the first particle, which remember is this one and this one, because it's up and down. And a second person, who we'll call Bob, could have the second particle, which is this bit and this bit. And they could take their particle a long way away from each other. And before they do anything, this is the description of the system, an entangled state. And let's say they go a very long way, a light year away from each other. They go to a distant star. Well, they wouldn't be a distant star, they'd be a very near star, but you know what I mean. They go a long way away. And then Alice decides to measure her particle, and she measures it pointing up. Then what that does is immediately collapses Bob's particle to up as well. So the state, or the direction of the arrow on Bob's particle is immediately being changed, instantaneously, faster than the speed of light. Okay, so for those of you who know about special relativity, it sounds as though this is a violation of that. It turns out it's not, but nonetheless, it's weird. Einstein hated it and could only call it spooky action at a distance, and he spent a lot of his later years trying to disprove it, but without success, and now we're pretty sure it's right. So what can we do with this? Well, Alice can do something that instantaneously affects something a long way away. This is another example of that non-locality I talked about, that bomb affecting the photon, the light that didn't go anywhere near it. Alice doing something to her particle instantaneously affects something over there. So how could this be useful? Well, the thing that springs to my mind immediately, and possibly some of yours, is teleportation. I mean, that's all teleportation is, right? You do something here, you affect something over there. I do something to myself, put myself in a transporter, and affect something over there, and make myself appear over there. So can we use these ideas for teleportation? I mean, ultimately, that's why we all go into physics, isn't it? For teleportation. So if we can do this, I mean, we're on to a winner. So this is my depiction of teleportation. Oh, that's not loud enough. Oh, we're going to have that again. Okay, so that's what we want to do, right? So there we are. We haven't done it yet. How do we do it? We do it. We have to make use of entanglement to do this. And I'm not going to be able to explain all the details. But effectively what we do is we start off with an object, a red dot, that we want to instantaneously transport to over there. And the way we do it is we create an entangled pair of particles between the two parties, the person sending and the person receiving. Now, remember, if we do something to this one, we can instantaneously affect this one. So if we do the right thing, then we could do the right thing to this one. So somehow we want to encode this onto this. So we want to do something to these two particles in such a way that this particle ends up over there. Now, I don't have time to go into the details of how that's done, but effectively we make a joint measurement of these two. So we measure the two together, and if we do it in just the right way, then we can turn these two into what that pair used to be, and we can turn that one into what that used to be, instantaneously, faster than the speed of light. So if you ignore the blue dots, just put a blank spot on it, you can see what happens. We start with the red dot here, and instantaneously we end up with the red dot over there. And so that's the idea, in a very sketchy way, but that's the idea behind quantum teleportation. You might ask, is this real? And the answer is yes, it's been done. It's been done regularly with particles of light and also with atoms and ions. And you might ask, is this a realistic prospect? Can it be done on meaningful scales? And again, the answer is yes. Here is an experiment that is probably going on tonight. It goes on most nights when the sun goes down over the Canary Islands. Quantum physicists get a bit jealous of astronomers who get to go to nice exotic locations, so these guys decided that they were going to set up their experiment in the Canary Islands because they needed clear air, don't get me wrong, they needed good wine and good beaches as well, but they needed clean air for the photons to be able to travel between La Palma and Tenerife, which are 144 kilometers apart. And they've set up an experiment where they teleport photons between those two islands, so instantaneously transport the quantum information from one photon to another between two of the Canary Islands. So pretty amazing, I think. Pretty amazing stuff. So, yep, we've got time. So something that gets a lot of headlines in this whole area of quantum technologies is quantum computers. In fact, this really was the motivation behind a lot of the field. There was a paper by Richard Feynman in the 80s where he suggested that computers or simulators could be made a lot faster by making use of quantum features, and that really spawned a lot of the field. So the idea is that maybe we could use some of this quantum weirdness to exponentially increase computational power. And this, after all, is the age of data and computers and so on. So if we can make computers exponentially faster, then we're really onto a winner. The applications are vast. Things from doing better fundamental science, well, that's of interest to us, but better weather forecasting. Weather forecasting requires huge computers, and it's still not amazing. It's pretty good, but it's not amazing. Drug design, you could get a computer to sort through every possible combination of molecule to find ones that will do just the specific job you want in a very short time. Better games, of course. Quicker Facebook status updates, all these things that are very important to us in life, we need them, and we need them now. We're impatient about things getting faster and faster every year. And quantum computers are a possible way of doing this. So there's been a lot of hype in the media about this, which is good for us, but sometimes can give people the wrong idea. Here's a Daily Mail headline from about a year ago. Google tries to save the world. Internet giant explains how its move into quantum computing could solve global warming. It's not completely wrong, but it's not completely accurate. As I say, weather forecasting uses big computers. Mark in the introduction said I'm from New Zealand. I know that the two biggest computers in New Zealand are the Met Service and Weta Studios, which is Peter Jackson's film studio that made Lord of the Rings and so on. They're the two biggest computers in New Zealand. So it'd be good for that, better films. Here's one from Yahoo, about just shortly after this one. The God Machine. Well, we've had the God particle. We're not missing out on the action. The God Machine. Labs race to build quantum computers which could save millions of lives. Stewart, I don't know who Stewart is, but Stewart is keen to point out, though, that machines will not be sentient, at least in the way humans understand it, nor would it be able to predict the future. So there are some limitations. Time. Cover of Time, no less. The Infinity Machine. We had the God Machine, the Infinity Machine. It promises to solve some of humanity's most complex problems. It's backed by Jeff Bezos, NASA, and the CIA. Each one costs $10 million and operates at 459 degrees, that's Fahrenheit, below zero, and nobody knows how it actually works. Actually, that last bit is not entirely untrue. There is a lot of debate about how these things work. I think we have a fair idea, but there's some controversial issues about them. So there's a lot of hype. Let me try and tell you some of the reality behind that hype. The truth is that they are very exciting and hold a lot of potential and could do some of the exciting things that the claims are making. So in order to understand them, let's have a look at our computer. Pretty old looking computer, this one now. All the magic happens inside the hard drive, which is this box that you see behind beside your screen usually. Take the side off, look in there, there's a circuit board. On the circuit board there's a chip. And on that chip, there are transistors. In fact, there's a lot of transistors, many transistors. And the way that the computer industry has taken off and really sped up is completely down to, or almost completely down to the fact that developments in fabrication and miniaturization of transistors on chips has just been phenomenal progress, and they're able to put more and more on them. And this is illustrated by a law called Moore's law. This was first put forward by a guy called Gordon Moore in the mid-60s, and he was one of the co-founders of Intel, you know, the big computer chip company. And he said that computers would get twice as fast every 18 months for about the same price. People often leave that last bit off, but it's very important. So for about the same price, computers get twice as fast every 18 months. And you know that yourself. You go down to your local electrical store with a fixed budget to buy a computer, you can be pretty sure that if you go back in 18 months, 2 years' time, you're going to get something twice as good for the same money, right? We see that. And this is a plot illustrating that, where years across here, from 1988 up to about the present day, on this axis, we've got the number of electrons that goes through each transistor. So going from 10,000 down to 1. These are in steps of 10, so it's going down very fast. And the numbers on each of the dots is the number of transistors put onto each chip. So 4 million in the late 80s, up to about 32 billion now. And another amazing advance has been the development of memory, which has been very important to computing. In 1974, I looked up, if you wanted to buy a megabyte of memory storage from IBM, it would cost you £400,000 for 1 megabyte. I looked on Google earlier today, and you can easily buy 1 terabyte, that's 1 million times more, for about 50 quid, easily. So if you scaled things and tried to buy 1 terabyte, I have fun playing around with these things, in the 70s, then it would correspond to approximately the US annual defense budget. So what you can buy for 50 quid now, in the 70s, cost you the US annual defense budget, which is not a small number. So that just illustrates, I think, the amazing advances in computer memory. So anyway, back to Moore's law, which is a similar amazing advance. This thing keeps going on, and you know, we keep wanting faster computers and faster Facebook updates and all the rest of it, but eventually we're going to reach a point where we get 1 or fewer than 1 electrons per device, and then what happens? You can't have less than 1. You know, we're well into the quantum regime. So this means that about 2025, some people say April the 17th, computers will get no faster. And we're just, well, actually that's not true. They'll get no faster for the same price. We'll be able to get faster computers, but we'll just have to pay more. And we don't like that. So what do? Well, I like this quote. I like this quote from the third man. Spoken by Orson Welles. I'll read it for those who can't see it. In Italy for 30 years, under the Borgias, they had warfare, terror, murder and bloodshed, but they produced Michelangelo, Leonardo da Vinci and the Renaissance. In Switzerland, they had brotherly love. They had 500 years of democracy and peace, and what did that produce? The cuckoo clock. So, you know, necessity is the mother of invention, it's saying, right? And science is always, through history, it's always been at its best when confronted with big problems. An experiment that showed a very surprising result, a technological need that was lacking. Actually, you know, war's not great, but war is another time where technological advances really go ahead, again, through necessity. So hardship is good for science, and, you know, the hardship of not being able to download that film in, you know, record time is going to cause people to try and find a better and faster way of doing it. And the way that has been achieved is through quantum computers. So, you know, I haven't got long, so I can't really tell you in any detail how quantum computers work other than to give you a flavor for it. And the flavor is that we know that objects can be in more than one place at once. So a single object can represent more than one thing at the same time. A normal computer takes an electron that represents a number, say 10, it passes it through a gate that might add 3, another gate multiplied by 5, etc., and does a whole sequence of steps that does a calculation. And then if you want to do it for another number, then you repeat all the steps again. In quantum mechanics, we know that an electron, or any quantum object, can represent lots of things at the same time. It can be in 2 places, it can be in lots of places at the same time. So it could represent every number from 1 to 100, every integer from 1 to 100 at once, or 1 to 1,000,000 at once. And then if you pass that through a single gate, you're effectively doing the +3 to all of those numbers. And then the next gate, times 5, or whatever I said, to each of those numbers. So by doing single steps with a massive parallel state, you're doing massive parallel computing almost for free. You don't need all the hardware to do it. You're not wiring up lots of computers. You're just making use of of the laws of quantum mechanics. So, you know, a very crude depiction of it is something like this, where you split this off into lots of different things and do a different computation on all of them and bring all those things back together at the end. Again, using the parallel universes idea, some people like to say that what we do is we have this computer here, and in a parallel universe I have another computer. So if I could just exploit that, I could send my calculation to copies of this computer in different universes, then I'd manage to do some pretty powerful computing. So that's the way of understanding it. So what can they do? Well, here are the two equations I promised you. These are the only two equations I'm going to show you. I think you probably are familiar with those or could work them out. These, I hope I don't disappoint you by saying, these are the cutting edge state of play of quantum computers at the moment. Quantum computers have worked these two things out. Hundreds of millions of pounds, 30, 40 years of effort, and that's what they've done. In fact, the first one was the headline in a Swiss newspaper. I don't know what the good people of Zurich thought when they picked up their morning paper and saw 15 equals 5 times 3. What are they telling me? But anyway, it did. It made the front page of the Zurich newspaper. But they've also done this one. So it's not so bad. It turns out that quantum computers are very good at factorizing large numbers. And the reason why this might be important is that internet security is based on this. So when you do your online banking, the security that ensures that nobody can get hold of your bank details is based on the fact that if I give you a very long number, so 100 or 200 digits long, and ask you to factorize it, so doing this but for much harder numbers, it takes a very long time. And in fact, it scales exponentially with the number of digits I give you. So each digit I add, it gets twice as hard. So if I add 100 digits, it's not getting 100 times harder, it's getting 2 to the power of 100 times harder. Okay? So to give you some idea of the numbers, in the 90s your internet banking was encrypted with 155 digits, and it was pretty safe because in those days it took 300 computers 7 months to factorize this. So your bank details were pretty safe. Now it would take 2 weeks for one standard desktop, and anyone who wants to break into your bank account is not going to be using one and is not going to be using a standard desktop. So it's going to be a lot quicker than that. So that would not be safe at all. So what you do is you add a few more digits. And Gmail, for example, has 617 digits now. And we can just keep going, right? Because each time it gets exponentially faster. So as long as computers grind to a halt, as I said they would, then we can always ensure security. The problem is quantum computers are an exponential speed up. So they completely cancel out the fact that this code breaking gets exponentially harder. And in fact, quantum computers would enable you to essentially bring down most of the current internet security protocols pretty easily. So it's a bit of a worry. But the good news is, it's funny how nature often works out this way. The good news is there's another quantum technology that is more mature called quantum cryptography, which is a way of encoding things and making them completely secure, so nothing could break them, not even a quantum computer could break them. And this is quite a mature technology. It relies on the fact that quantum systems, if you try and measure them or try and look at them, you change them. It's completely unavoidable to change them. And so if somebody sends a message using a quantum system and you try and eavesdrop on it or try and skim a bit off or try and look at it, you will leave a record that you've looked at it. And so you can always spot an eavesdropper. And there are commercial products that do this. There's a company, Magic, that makes these. You can send emails now in a quantum encrypted way. You can stream video. The Swiss, they're quite advanced with these things. Their elections since 2007, they've collated all their election results in a quantum encrypted way. The FIFA World Cup in South Africa, I was lucky enough not to be at the World Cup, unfortunately, but just after it, I was in Durban in 2010. And I saw their stadium here, beautiful stadium. They'd created a network of a security communications network that was all quantum encrypted between the stadium and the security at the stadium and the police force downtown and so on. They're this completely secure quantum encrypted network. And there are financial institutions in the city that send quantum encrypted information between them, particularly sensitive information. So this is quite a mature technology. I think I should start to wind down. Let me another 5 minutes, or yeah, another 5 minutes. Okay, so very quickly, metrology. The last application I'm going to talk about tonight. This uses, I only want to talk about it because it's something dear to my heart, really, but it uses something called squeeze light, which is not this, but it's a quite esoteric quantum effect, which I won't say any more about, but you can do funny things with light to make it very good at imaging things and at measuring things in a really precise way. Why might we want to do that? Well, mainly for fundamental science. If you can do better science, I mean, all of science is based on measurements. Measurements enable you to distinguish different theories. And so better measurements reveal a deeper depth of detail. So I don't know if you've seen this before, but for most of you that should look like Marilyn Monroe. But if we blow it up and give a bit more detail, the same picture, it looks like someone else. And if you sort of put your eyes a bit out of focus, maybe it'll go back to Marilyn Monroe. So being able to distinguish Marilyn Monroe and Albert Einstein might be important in some context. So better measurements are a good thing. So they're also good for developing things like atomic clocks, and a number of my colleagues work on atomic clocks, trying to develop quantum clocks. I always annoy them by showing them that in our tea room, until recently, we had a clock that looked just like this. It was a quantum clock. They don't like me telling them that we already have one in our tea room. But we do. That's quite different, of course. It's also very important for GPS systems. So, so your sat-nav is very good. This relies on very accurate clocks. Power grids. I was surprised. I was at the National Physical Lab recently, and they said that a lot of our power supply is based on incredibly accurate timing between different servers and so on. Micro trading. A lot of trading of stocks in the city is done automatically now, and people pay a lot of money to have their computer close to the server to gain valuable microseconds. And it's very important to be able to put a timestamp on every trade so that you can tell who was first, who got in first, right? So it's very important to have accurate clocks. And in fact, NPL is, I think it's quite intriguing, they're selling time to the city. One of their big industries at the moment is they sell accurate time to the City of London so that they can tell who got their trade in first. And I think it's intriguing because some of you may know that this used to go on in London in Victorian times. This is Ruth Belville from the Belville family. Does anyone know about her? She was known as the Greenwich Time Lady. And from she didn't do it all this time, but the family from 1836 right up until 1940, which is incredibly late, used to sell time to people in London. They'd go with their pocket watch to Greenwich, get the accurate time of the day, and they'd go around to whoever needed accurate time, train stations, whoever, and sell them the accurate time for that day. And NPL are doing the same thing again. So it was only 60 years that this industry didn't go on in London, and it's back on, which I think is quite nice. Another idea is being able to probe some interesting aspects of fundamental science, such as testing Einstein's predictions about general relativity. Now, Einstein tells us that when an object moves, it creates ripples in space-time. So if I walk across the room, they're tiny, but I'm creating ripples in space-time. If you have a really big event, like a supernova, then that can create bigger ripples in space-time. They're still incredibly tiny, but it's one of the predictions of general relativity, and it's something that we'd quite like to test. And there are these great big devices, they're interferometers, they're very similar to what I showed you with beam splitters before, you know, the quantum bomb and all of that. There's a huge one in Washington State, another one in Louisiana. They're about 4 kilometers long, these arms, so they're very big. And they're trying to measure incredibly small fluctuations. Look at this, distance, the ratio is being able to measure the distance around the world to within 1/10 millionth of the width of a human hair. Incredible precision they need. And they're currently making use of quantum states to try and get close to those sort of precisions they need. So there's some really interesting things going on. I think that's probably a good place to end. I hope that I've given you a flavour for quantum physics, some of the weirdness. I hope I've shown you that it's not so difficult and not so hazy. There's going to be some really interesting developments in this area in the future, I'm quite sure. I'll leave it to Niels Bohr to tell you what they're going to be. But the takeaway message is that quantum physics is weird. It really does challenge the way we think about the world, but it's going to have a big impact on the world pretty soon. going to have some problems too. I didn't talk about them, but it's going to potentially have some problems. And there's lots of questions left unanswered, so there's lots of interesting physics for me and students and various other people to do too, which is always good. So thanks very much, everyone.
Thanks very much, Jacob, for a great talk.
Thank you.
So I think we have some time for questions, which I do hope that Jacob won't leave unanswered, or at least so if you'd throw the floor open, and if anyone likes to ask a question, stick their hand up. So,
you could hand the microphone even. You could be sort of Jeremy Kyle style.
That might be it might mean a lot of running.
Very simple question. When you were talking about putting larger and larger objects through slits and getting interference, intuition tells me that you have to have bigger slits. Is that true?
So yes, you're right. The geometry of the slits is very important, and as you make the slits very large, then you'll find that the light just goes straight through it. And you see this with water waves actually. If you have a barrier in the sea and water waves come in, and the slit is very wide, much relative to the wavelength, the distance between wave crests, then the waves essentially go straight through. It's like a beam of light or a stream of waves. And as you make it smaller and smaller, then they spread out. They really bend around that corner. It's called diffraction. And so you're right, as you make the slits smaller and smaller, these beams will diffract out and overlap and interfere. So there is, as you say, quite a lot of influence of the geometry, and if you made the slits very wide, you're right, you would just see two spots on the screen. Things wouldn't diffract, they wouldn't interfere, you'd see something quite different, and you wouldn't see these quantum effects. So it is important that you arrange things the right way. Did I answer your question? Okay, do you want to follow it up?
What I really wanted to know is if you're doing bigger and bigger objects,
from
the electron to the photon,
okay.
do you have to have a bigger slit? Presumably it has to be of the order of the wavelength of the object.
Okay, yes, okay. Yeah, very, very good question. What you need is that the object needs to be able to fit through it, so you can't have a slit that's smaller than a protein size if you're going to fire proteins through it. But the key thing is that light can behave as a particle and a wave, and similarly particles, things like atoms, can behave like waves as well. And if we cool them down, which is what is done with these experiments, then they behave like waves. And so the key thing is, what is the corresponding wavelength of that particle when it is treated like a wave? And typically, the wavelengths for these things are actually a lot smaller than the wavelength of light. So actually, counterintuitively, I mean, your question was very good, but counterintuitively, you can get away with smaller slits, as long as they're not narrower than an atomic width, otherwise the atom wouldn't get through. But as long as they are small, comparable to the wavelength of that object. So the wavelength scales inversely with the mass, so the bigger the object, the smaller the...
Might not need it. You mentioned that there was a 90-degree phase change on reflection.
Yeah.
It's been a while since I did physics, but I teach my A-level students that there's a 180-degree phase change on the outside surface and nothing on the inside.
Yes, correct. Oh no, it doesn't work. No, you're absolutely right. So if you reflect head-on from a surface, you get a 180-degree phase change. If you have something inclined and you work out the boundary conditions and so on, you've got a component. This is a very hand-wavy argument that's not quite right. You get a component that you can think of as going through and a component that you can think of as being reflected. So you get 180 for some of it and 0 for some of it, and the net effect is 90. That's an inaccurate explanation, but hopefully it gives you an idea. So the angle of incidence is important. Yeah.
When you get to something as big as protein, it's going to have different shapes, isn't it?
Yes.
So, is it like a cat? It slithers through?
Yeah, so That's right. It turns out to be incredibly difficult to deal with complex molecules, not just because they're bigger, as you say, but because of the structure they have. And you want to make sure that things cannot be distinguished. There's an important concept in quantum physics of indistinguishability. Two things have to look identical. So molecules have lots of what are called degrees of freedom. They can vibrate in different ways, they can be arranged in different ways, and those are things that can distinguish two proteins. You could have one wobbling and one not wobbling, for example. So you have to be very careful to try and ensure that they can't be told apart, which usually involves cooling them down to very low temperatures. And if you get them to sufficiently low temperatures, you get all the vibrations out of them. You suck all that energy out. And then they start to behave as waves. And as you make them colder and colder, those waves get bigger and bigger. And what happens then is that all the individual structure of it smears out. It's like putting a lens out of focus. You're making it all into a wave. And suddenly you've got this sort of nondescript sort of blob, if you like. And then you don't have to worry about the structure so much because it's all out of focus. You can't see it anyway. So that's the key. It's hard. You're absolutely right. It's hard. And the way you go about doing it is by making them very, very cold, which is another talk. Yeah, maybe another IOP time I can talk about making things cold. That's something that I'm particularly interested in.
Question up there?
You know that diagram you had where you had photons across the two ways. How can you be sure that the photon actually goes two ways? How can you like experimentally show it?
Okay. So the answer is that if we try and measure it on either of the paths, we see it on one of the paths randomly, because maybe I should, let's see if I can find it, because then it's just, where's my cursor? Oh, I'll just, because then it's just a beam splitter, right? Where are we? So, yeah. One of these, right? Let's go back to. So here. So if we have, so if we put a detector on this path or this path, then what we'll see is we'll see a photon on one of them, randomly one or the other, because you can ignore the rest of this. A photon comes in, and remember, it randomly goes one way or the other on this. So we always see the whole photon here or here when we make a measurement. Okay, so we always find it in one universe or the other. Or another way is we always find it on one path or the other. How do we know it's on both? Well, that's an interesting question. We know it must be on both because there's no other way we would see interference. If it was definitely on one or the other, then when it gets to here, it would 50-50 go out either of them. So you kind of have to infer retrospectively, although there are some interesting experiments that are able to use something called weak measurements to try and infer, to image, to get some average information about which path they're on, and you find that it is on 50-50 if you do those, but that's quite an esoteric thing. Essentially what you've got to do is rely on the fact, wing and a prayer really, rely on the fact that there's no other way you would get this result out here. So it's a weird result. We've got to explain it somehow. We can talk about parallel universes. We can talk about objects being in two places at once. Take your pick. But the fact remains we're seeing something weird there.
Okay, thank you very much. I think time to wrap it up. So let's first of all let's thank Jacob again.